All right, welcome to the second half of our part 2 of our lecture video series for Wednesday, April 26th. We left off, we were trying to figure out the heat of reaction, and we know that the heat of reaction for this particular precipitation reaction and all heats of reaction in general are always calculated per mole of product or sometimes even mole of reactants that's reacted. So we were able to get the amount of heat that our reactants had to have absorbed. And now we need to figure out how that amount of heat can be put into proportion with the amount of moles of product that are formed. So if we're trying to figure out how much of a product is formed in a chemical reaction, we need to do some stoichiometry. So let's determine our moles of precipitate formed. So in order to do that, we need a limiting reactant calculation. So let's take a look here. I have some information about each of my reactants. And if you notice, luckily for us, it seems like because we had equal volumes and equal concentrations, and this reaction happened in a 1-to-1 for each reactant, that whatever many moles was contained of one is going to be equal to moles of the other, meaning there is no limiting reactant here. So sigh of relief, yay, no limiting reactant. We just need to figure out our theoretical yield based on our volume and concentration. All right, so let's see here. We have a 1-to-1 reaction of equal volumes and concentrations of reactants. So there's no limiting reactant. Let's go ahead and start with a volume of 1. It doesn't matter. So we had 25 mils of, let's do the sodium carbonate. And let's see here. I was given a concentration in 2.00 moles per cubic decimeter. Well, that's a bummer because milliliter, remember, is really just a way of saying centimeter. So I'm just going to cross this out and say cubic centimeter. And notice if I were to just do this calculation as is, cubic centimeters and cubic decimeters would not cancel. So I need to be left with cubic centimeters in the denominator so that I can cancel out my decimeters. And since I don't know how many cubic centimeters are in a cubic decimeter off the top of my head, I'm going to use their just kind of normal one-dimensional relationship in order to get this going. So a quick way to figure out relationships between like deci and centi or million kilo, without having to jump between your kind of base unit first, is you can write out the equivalence about what you know about each. So for example, I know that 100 centimeters makes up 1 meter, and I know that 1 meter is also composed of 10 decimeters. So I can make the equivalence that 100 centimeters is 10 decimeters, and if I cancel out a 0 on both sides, 10 centimeters is 1 decimeter. So 10 centimeters is 1 decimeter. And if then I were going to cube this, I would have to cube both my unit and my value. So 1 cubed is 1, 10 cubed is 1,000. So I would need to take my 25, multiply it by 2, that gives me 50. divide by 1,000, that gives me 0.050 moles of the sodium carbonate. And then let's look at our mole ratio between sodium carbonate and the magnesium carbonate. So it looks like that's 1:1. You want to do this based off your net ionic equation, so that's a lot clearer. I think that's a good idea. So I know that for every one mole of sodium carbonate reacted, I create 1 mole of my products. And I do not need to do this calculation again for my magnesium nitrate because, again, I know that this reaction is all 1:1 and I've got equal volumes and concentrations, meaning that I have the same number of moles of each, so neither is limiting. So this makes 0.050 moles of my magnesium carbonate product. So then let's find the heat of reaction. This is going to be the heat of my chemical system, which was my reactants, over moles of product. So that is my 1255.2 joules of heat that was absorbed by my reactant per 0.050 moles of product that was formed. So when we do this, we get, well, let's see here. I've got some rounded numbers in my notes. Let's not do that. This is 25,104 joules per mole. Expressed in kilojoules per mole, I think is probably a little bit better. So this becomes 25.1 kilojoules per mole. And this is the heat of this reaction. And notice, this is a positive sign. So this means that this is an endothermic reaction. This required heat in order to make the precipitate, which makes sense when you go back to our raw temperature data, right? The surroundings got colder. That's because some of the heat that was in the surroundings, some of that thermal energy, was transferred into the reactant particle system to create the precipitate. So since that reactant particle system required energy, it absorbed energy, that is an endothermic reaction. So this is how we can determine the heat of reaction empirically or directly by using calorimetry. We're going to be doing this a lot, so if this seemed like a big fat example, it's because 1, it is, but also 2, it's something that we're going to be practicing in lab coming up in the future, so don't worry, you will get your practice in. So that wraps up part 2 of this lecture video series. Let's move into part 3, which is looking at the standard heat of formation and how that can allow us to figure out the heat of reaction purely on a theoretical basis. So we're no longer looking at calculating heats from masses and specific heat capacities and temperature changes, but rather we are going to be doing some purely theoretical determinations of the heat of reaction by looking at what's called the standard enthalpy of formation.